Coming to case 3 of convex lenses. In the first case and the second case, the object was at infinity. Now the object is coming closer to the lens. Consider case 3 where the object is beyond 2f1. 2f1 is also known as C1, that is the center of curvature, first center of curvature. Object is beyond C1, that means it is behind C1. Here is the object. So if we draw the object, this is the object. One ray from the head of the object hits the lens. It is refracted and it goes along this path. Another ray always passes through O. Whichever ray passes through O does not bend, it goes undeviated. The two rays of light are meeting on the right hand side and they form an image here as it is shown at B1. This is the image. And if you can see, the image formed is slightly smaller than the object we had placed here. So AB is the object, A1, B1 is the image formed on the right hand side. Writing the characteristics of the image formed, since the rays of light are actually meeting and the image is formed on the right hand side, it is a real image. It is an inverted image. Remember, real image is always inverted, and it is diminished because it is smaller than the object. Also, it is formed between F2 and C2 on the other side of the lens. The use of this case is in photographic cameras. This particular case of the lens is used in photographic cameras. Case 4. The object is coming slightly closer and now it is at 2f1, that is also known as C1. So AB is the object which is placed exactly at C1. One ray of light from the head of the object passes through the lens. It is refracted and it goes along this path. Another ray of light always goes through O, which goes straight without any bending. Both the rays meet at a point and we get an image formed exactly at 2f2 on the other side. This is a special case when the image is at 2f, object is at 2f1, it forms an image at 2f2. Remember, the image will be always same size as the object in this case. Again, image is formed on the right hand side. It is real. Since it is real, it is inverted. It is the same size as the object and it is formed at C2 on the other side of the lens. This case of the convex lens finds its use in a terrestrial telescope. Next case. The object is still coming closer. Now, as you can see, the object is between F1 and 2F1, that is if we draw the rays, this is our object between F1 and 2F1. A ray of light from the head of the object goes straight, hits the lens, it is refracted and go along this path. Second ray of light straight passing through O, undeviated. Both the rays meet at this point and here we get an inverted image. Remember, the image is inverted since it is real. Also, the image form is magnified in this case. So if this is the object, this is the image which is slightly bigger than it. Again, characteristics of the image is real, it is inverted, it is magnified and it is formed beyond C2. Beyond C2 means it is formed behind C2 or 2F2 on the other side of the lens. This case of the lens finds its use in cinema projectors. Next case, case 6. Now the object is coming closer, still closer, and it is exactly at F1. As you can see, we place the object at F1. One ray of light from the head of the object hits the lens and it passes through F2 like so. Another ray of light goes straight through O, and as you can see, when you draw the diagram, both the rays are going to be parallel to each other. The parallel rays never meet, so we say that the object is formed at infinity. Although we cannot see the object, but we say that it is formed at infinity and it is highly enlarged or highly magnified. Again, characteristics, the image is real, it is inverted, it is highly magnified. Remember, an image that is formed at infinity is always highly magnified, and it is formed at infinity on the other side of the lens. This case of the lens finds its use in searchlights and spotlights wherever we require a parallel beam of light. Case 7. The object is coming still closer. Now the object is between O and F1. O is the optical center, F1 is the first principal focus, and we are placing the object here. First ray of light from the head of the object passes through the lens, goes from F2. Second ray of light from the head of the object passes straight through O. Now if you can see, these two rays of light are deviating rays of light. They are diverging. Both of them are diverging from each other. So they are never going to. But we can also identify that if we pull these rays backwards, they will meet at the some point. So we pull them backwards and we make them meet at a point. Wherever they meet, it forms a virtual image, A1B1, and the image is magnified as you can see. Now in this case, the image is formed on the left hand side. This image is virtual. Since it is virtual, it is erect. Also, we can see that it is magnified and it is formed on the same side as the object. This case of a convex lens is the most important case. It finds its use in simple microscope to observe biological specimens, and it is also used as a magnifying glass to read small alphabets in a dictionary or to read any kind of small print or to see any kind of microscopic objects, because it gives us a virtual and an enlarged image. So if we go back to all the cases of convex lens, we can identify that for a convex lens, we have 7 cases, as you can see, till case 7. Cases 1 to 6 form a real image, while case 7 forms a virtual image. Also, from case 3 onwards, whenever we are drawing a ray diagram, we should be careful that we are taking equal distances on both sides. By equal distances, I mean from O to F1, if you take 2 centimeters, from F1 to 2F1, again you shall take 2 centimeters. Same thing on the right hand side. From O to F2, you shall take 2 centimeters. And from F2 to 2F2, you shall take 2 centimeters. If you take same distance on both the sides, drawing of the image will be perfect. You are going to get an image perfectly where you want it to be. So be careful. This thing does not happen in case 1 and 2, because case 1 and 2, the object is not fixed, it is at infinity. But from case 3 onwards, for case 3, case 4, case 5, 6 and 7, we are supposed to take perfect measurements on both the sides of the lens starting from O, like I showed you. So here we finish all the 7 cases of convex lens. Coming to the images formed by a concave lens. For a concave lens, we have only 2 cases. Case 1, which is very similar to the convex lens, the object is at infinity. So if we have rays of light coming from infinity, two rays of light are coming from infinity. After passing through the concave lens, they will be diverging as shown. Now the divergent rays never meet, so they are not going to form an image in front of the lens, but we can make them meet at the back. So we pull them backwards with a broken line, make them meet backwards, and behind the lens, that is on the same side of the object, at f2, these rays are going to make a virtual image. A virtual image is always drawn with broken lines. So at f2, it forms a virtual image. As we can see, these are diverging rays, they are not meeting, so we are supposed to pull them backwards. If we write the characteristics of the image formed, the image is virtual. We know it is virtual because it is formed on the left hand side behind the lens. Since it is virtual, it is erect. It is also diminished to a point, very much point-like, and it is formed at f2 on the same side as the object. This case of concave lens finds its use in a Galilean telescope. Case 2. The object is anywhere on the principal axis. So in this case, we are going to take perfect measurements, that is 2 centimeter each, starting from O. An object is placed anywhere on the principal axis, but we are not going to put it very close, otherwise formation of the image would not be very clear. So we are putting it slightly away from the lens, but anywhere on the principal axis. This is the object. A ray of light from the head of the object passes through the lens and it is diverging. Another ray of light goes straight through O without any kind of deviation. Any ray that passes through O always goes straight. Now we can see that these rays are not meeting anywhere. So for the formation of the image, we are going to pull this ray backwards. The divergent ray is pulled backwards and made to pass through F2. Now we can see both the rays are meeting at a point, and here is where the image is formed. A1, B1 is the image formed. Again, the image is formed on the left hand side by pulling the ray backwards, and hence it is a virtual image. So if we talk about the characteristics of the image formed, the image is virtual, it is erect, it is diminished, and it is formed between O and F2 on the same side as the object. This case again is an important case because it is used for the correction of short-sightedness or myopia. Whosoever has specs, whosoever suffers from short-sightedness, it is a defect of the eye, will always have a concave lens in their spectacles. So we are done with the images formed by concave lens as well. Only 2 cases for concave lens and 7 cases for convex lens. Now, memorizing these cases is very important because we have to remember on which side of the lens the image is formed. That is, the image is formed on the left hand side or on the right hand side in a particular case. How is the object, whether it is erect, how is the image, whether it is real and inverted or virtual and erect, plays a very important role in solving the numericals for lenses. Before we start with numericals, there are few things that we are supposed to learn or remember. The first concept is that of a linear magnification. Linear magnification is given by 2 formula. It has 2 equations. M is equal to size of the image upon size of the object. Size of the image is known as HI. It denoted as HI, and size of the object is denoted as HO. So it is HI upon HO. I write it here. So magnification M is equal to HI upon HO. It is also equal to V upon U. So remember 2 equations for magnification. M is equal to HI upon HO and M is equal to V upon U, where U is the object distance, it's mentioned here on the right hand side, where U is the object distance from O and V is the image distance from O. Hi is the height of the image, Ho is the height of the object. Now we should remember that when we say magnification, magnification does not only mean that the image is enlarged. Magnification can also be used in the case where we have a diminished image. So, if magnification is greater than 1, the image is magnified. That often happens in numericals, that when we are solving a particular sum, we get m to be greater than 1. If the magnification is greater than 1, then we should understand that the image is magnified. While if magnification comes to be less than 1, we have to understand that the image is diminished, particularly when we have to write the characteristics of the image form. For example, if the image is 3 times magnified, then we take to be m is equal to 3. But if the image is 3 times diminished, we take m to be 1 by 3. Understand the difference? We also have to learn lens formula, which says that 1 upon f is equal to 1 upon v minus 1 upon u, where f is the focal length of the lens, u is the distance of the object from the optical center, and v is the distance of the image from the optical center. So, in all, we have 3 formula to remember. M is equal to Hi upon Ho, M is equal to V upon U, and 1 by F is equal to 1 by V minus 1 by U. 3 formula to remember. A special case of convex lens that we are supposed to learn independently is when it is used as a simple microscope. We just did the cases and we know that this is the 7th case of convex lens wherein it forms a virtual and a magnified image. So it is the same 7th case. As you can see, object is between O and F1 and the image is formed behind 2F1. The image is formed behind the lens, that is at the same side as the object, by pulling the rays backwards, and hence this is a virtual and a magnified image. The uses of a magnifying glass are important. It is used as a reading glass. It can be used to observe the weaving patterns of a cloth. It can be used to observe the lines of a hand by palmist, and it is also used to read a vernier scale. Few things about a lens. Power of a lens. How do we define the power of a lens? The reciprocal of focal length in meters is known as its power. That is a particular definition, wherein for power we have to use focal length in meters only. But if your focal length is not in meters, in order to convert it, we will change the equation to 100 upon f. So, power is equal to 1 upon f if f is in meters, and power is equal to 100 upon f if f is in centimeters. The SI unit of power is diopter, that is capital D. Also, 2 things to remember. For a convex lens, power is taken to be positive, while for a concave lens, the power is taken to be negative. We are supposed to memorize this. For a convex lens, power is positive. For a concave lens, power is negative. Now, if you talk about a combination of lenses, suppose you have a convex lens of focal length 75 centimeter and a concave lens of focal length 40 centimeter. We find the individual powers first. So, the power of the convex lens will be 100 upon 75 according to this formula for power, 100 upon f. So, 100 upon 75, that 1.33 diopter with a plus sign because it is a convex lens. Power of the concave lens will be 100 upon 40. That will give 2.5 diopter with a minus sign because it is a concave lens. Now, if both these lenses are placed in contact, we make a combination of these 2 lenses. The combined power P will be equal to P1 plus P2. If we add them, we get to be we get the answer to be minus 1.17 diameter. Now, since we are getting a minus sign, we can conclude that the combination of this particular convex lens and the concave lens behaves like a diverging lens, which is a concave lens. A combination of this particular convex lens of focal length 75 centimeter and a concave lens of focal length 40 centimeter is behaving like a diverging lens, that is a concave lens, because we get a minus sign in the answer, and minus sign indicates that it is a concave lens. That was all about power of lens, an important topic. And the last thing before we start with numericals is we have to memorize or understand sign convention. Again, two important things. For a convex lens, focal length is taken to be positive. For a concave lens, focal length is taken to be negative. We are going to define 5 parameters for each case of both the lenses. U, that is the object distance. V, that is the image distance. HO, that is the height of the object. And HI, that is the height of the image. Also M, which is the linear magnification of the image. Cases 1 to 6 for the convex lens, where it forms the real image. U, that is the object, is always on the left hand side, and hence U is taken to be negative. Object distance will be negative because it is on the left hand side of the lens. Image is real, which is formed on the right hand side, and hence image distance V will be taken to be positive. Please remember, all the parameters on the left hand side of the lens are negative. Parameters on the right hand side are positive. If we talk about height of object, object is always above the principal axis, and hence height of the object is positive. All the parameters above the principal axis, all the heights above the principal axis are positive. All the heights below the principal axis are negative. So the image formed is real, hence it is inverted and is below the principal axis. So HI will be negative. Magnification in this case will be negative because magnification is HI upon HO, that is a minus upon plus, that is negative. Last case of convex lens, that is case 7, which forms a virtual image. U, object distance left and right, we are going to check left and right. Object is on the left, object distance negative. Image is on the left because it is virtual, image distance negative. Height of the object and image should be above and below the principal axis. Height of the object above the principal axis, positive. Height of the image above the principal axis because it is virtual and hence positive. Magnification in this case, positive, because HI upon HO, positive upon positive gives positive. Concave lens, both the cases form virtual image. U, object is always on the left hand side, so U is negative. V, image is also on the left hand side because it is virtual and hence V is negative. HO, height of the object, object is above the principal axis, so HO is positive. HI, image is above the principal axis because it is virtual, hence HI is also positive. So magnification in this case, M is positive because HI upon HO. So these are the sign conventions we are supposed to memorize before we start with numericals. Even if you do not memorize the table, it is better if you remember all the cases of the convex lens and the concave lens. That helps us to solve the numericals. Again, convex lens, case 1 to 6 give a real image that is on the right hand side. Case 7 gives a virtual image that is on the left hand side. Concave lens, both the cases gives virtual image which is again on the left hand side. Sign convention, depends upon whether the image is on the left or on the right. It also depends upon whether the image is above the principal axis or below the principal